Hello everyone, welcome back to my organic mechanism talk. Today we will talk about the hydroboration oxidation. First, we will talk about the normal hydration of alkene catalyzed by acid. So the normal hydration of this alkene actually give you the Markovnikov product. That means if you have these two vinylic carbons, if they are different, for example, this vinylic carbon has two hydrogens and this vinylic carbon has just one hydrogen. So the vinylic carbon with more hydrogen will take the proton at the first step in the mechanism. So that's called Markovnikov product, and that is a Markovnikov rule. Let's look at the Hydroboration mechanism of this reaction. The first step is actually the protonation. This is a proton because this is acidic condition, so that's acid. And then the pi electron from this alkene will attack this proton. That's called a protonation. And this carbon with more hydrogens will take this proton. So this carbon will be the positive charge. That's carbocation will be attacked by the nucleophile, the water. Water will share the lone pair of the oxygen with this carbocation to form this positive charged intermediate. And then another molecule of water will act as a base to deprotonate the proton to form a neutral product, and which is this isopropyl alcohol. And this is the secondary alcohol. And under this normal acidic condition, that is the product that's called a Markovnikov product. But sometimes if you want a primary alcohol, if you want a different product, and then you need to use a different strategy. So for example, you can use this hydroboration oxidation, and then you will make 1-propanol. And that is a primary alcohol. So this mechanism will be different. So I will show this mechanism step by step in next slides. Okay, so again, now this hydroboration oxidation sequence will give you an anti-markovnikov product, okay, which is to give you a primary alcohol if you use this terminal alkene. Now the mechanism, first step shown, the alkene react with the boron here, BH3 is called a boron, and boron here is electrophilic because it has an empty p orbital. The boron here actually has an incomplete octet, only 6 valence electrons. So the pi electron from this alkene will attack this boron, and then at the same time, the hydride here on the boron will actually shift to this carbon. So this gives you the propyl boron as the neutral intermediate. A general name is called alkyl boron. And you still have 2 hydrogen on this boron. They actually can do further hydroboration, again, with another molecule of this alkene, the propene. And then the pi electron will attack this boron again, and the hydride will migrate to that carbon again to make a dipropyl boron. And general name is called dialkyl boron. And now they still have a hydride here, so another molecule of the propene will react with this boron again. Follow the same pattern. Pi electron attack this boron, hydride go back, shift to this carbon to form a tertiary, trialkyl boron. Okay, so this is the tripropyl boron. Now this is the intermediate of the first step, hydroboration. Then the second step is the oxidation by the hydrogen peroxide under basic condition. Now the base actually will deprotonate the hydrogen peroxide to form a hydrogen peroxide ion, which is a negative charge on oxygen. This is nucleophile, and this will attack this boron because the boron is still electrophilic, still has an empty p orbital. So that give you the intermediate shown here. So negative charge on the boron. Now the propyl group, the alkyl group on the boron actually will migrate to oxygen at the same time, kick off this hydroxyl group as leaving group, break the oxygen-oxygen bond. Now give you this intermediate. You can see the intermediate compared with this, the tripropylborane actually has an oxygen insert between the boron and the propyl group. And you can repeat this two step twice again under this same condition. You will make borate. This is a tripropylborate. You can see all boron carbon bond were inserted by oxygen. And this borate will be hydrolyzed under the same condition to form the byproduct boric acid and the 3 equivalent of propanol. It's 1 propanol, and that is the primary alcohol, and that is anti-markovnikov product. That is our pushing mechanism of this hydroboration oxidation of the alkene. Let's talk about the hydration of alkynes. You may see an example I use. This is propine. It's a terminal alkyne, and under the acidic condition, the hydration will give you a ketone. This is acetone, and the mechanism actually are very similar with the hydration of alkene under acidic condition. So this is the arrow portion, and this is the proton from the acid, and first step is the protonation. So this also follow the Markovnikov rule. So this carbon, sp hybrid carbon with 1 hydrogen, will take the proton because the other sp carbon has no hydrogen. So this first step give you the vinyl cation. So it's not a very stable carbocation. It will attacked by water, which is nucleophile here, and form the intermediate, which is protonated enol, and water will depronate the proton and form the neutral intermediate, the enol. It's called enol, and enol will undergo tautomerization in 2 steps. First step is the lone pair from the oxygen will push back to form a pi bond, and that pi bond between these 2 carbon will take the proton, and then the intermediate is this protonated acetone, and the water will depronate the proton and then produce the neutral product. That's the acetone, and it's ketone. It's the hydration of alkyne under this normal acidic condition. Now what about the hydroboration oxidation of alkyne? Again, we will use this the terminal alkyne as example first. Okay, this is a propine. Under this hydroboration oxidation sequence, the product actually will be an aldehyde. Okay, the mechanism, first and second step mechanism will be similar with the alkene, so I'm not showing that again. So it take long steps. The alkyne will follow anti-Markovnikov rule here, give you the enol. So you can see this carbon with less hydrogen will take the hydrogen, and the other carbon with more hydrogen take this hydroxyl group. So this is an anti-Markovnikov intermediate, enol. This enol will also undergo tautomerization, but this time it's a basic condition. So the base will depronate the proton first, form this negative charged intermediate. It's an oxide here, so it's also called enolate. And enolate actually have this resonance. So if you push the negative charge, the electron from oxygen back to here to form a pi bond, and then the other pi electron will push to the carbon, form a carbon anion here. This is also called enolate. Both are called enolate, and this enolate will be protonated, okay, by the water. So this take the proton from water will give you the neutral product. The final product is aldehyde. It's a propanol. Okay, so if you want aldehyde, you can use the terminal alkyne react with the borane followed by oxidation. Now, if you use internal alkyne, the product will still be ketone. So, for example, if you use the 2-butane, and then after the hydroboration oxidation, you'll form this enol. But after the tautomerization, this will give you a ketone, not aldehyde. Okay, so that's all I want to tell. And if you have any questions, again, please let me know. Okay, good luck.